Hello, this is a video covering the development concepts needed to work with QEMU, and specifically the TIVA emulator we built at the end of this semester. So in this video we will discuss devices and sysbus devices, the device creation process, and then machines. In another video we will cover GPIO and IRQs. So devices versus sysbus devices. A device is just a container for emulation that QEMU uses. It handles input and output via the QEMU IRQ, which is like a wire almost. And sysbus devices are a special kind of device that have built-in IRQ systems for NVICs. Interrupts and exists in a space in memory, like the ADC, which exists at hex 4003, 8000. So there are a few main concepts for devices. There's the device state struct, object declaration, properties, VM state, the types and type info, and then class and instance initialization. So the device state struct holds data for each device. It has like the properties. It has a reference to the parent object, like this, and then any state information and output IRQs. So, for example, over here we have a regular device. This has one output IRQ, which is the GPIO pins we talked about earlier, and then a number for the property for its number of lines. And then the parent device. And then over here we have the analog state, which has 12 output IRQs, one for each of the AAN on the device, on the TIVA emulator. And then there's the voltage in and AAN variables. And sysbus devices also have a memory region, usually for their IO memory. And then, this servo state also has a clock, a timer, some booleans, and some other stuff. This is where all the device's information is stored, basically. Next, object declaration. This is usually done in the header file right after the struct is defined, and it will declare the device initialization functions, as well as links the device state struct to the device itself. And then this one here uses declare instance checker, which just ensures that the the test analog device returns an analog state and is named type test analog. But this is where you define the object for use in the C file. For the properties and VM state, so properties are designed to stay mostly constant and can be defined by other devices that are creating the device and using it. They usually have default values. You can see here, this is a uint8 type called uart. The property is called uart of the uart state struct. The variable is uart, and then the initial value is 0. So they define properties of the device. They have default values again, and you would use a special command. I think it's qdev prop set, something like that, when you're creating a device to set these values if you needed to. And then the VM state is very similar, but it just defines how the device is managed in memory and is used for things like memory migration, which I don't think is very important for our use case, but just in general, it defines, it has the name, its version, and then the different fields that it has. So now we're going to move on to the process for creating devices. This is the general process that QEMU does and what you should follow. So first, this always runs by QEMU. When you start up the program, it'll define any type and run the class initialization. And then when you go to create a device, you will start with instance initialization, which is when you call QDevNew. And then if you need to, you can realize it using realize it unref. And then then QEMU on its own will call the device reset after the realization. So first, let's talk about the types and the type info. So every device is going to have type info that will tell QEMU what the name of the device is, what the parent type is, the size of the instance, which is the size of the state struct, and then pointers to the initialization functions for both the instance and the class. We also use this function here. This is kind of like a standard stamp almost. You just register as static the type, and then you call type init on it. Note this is not a function. There's no semicolon. This is like a macro or something. Now we'll go on to class initialization. So this is where class properties are initialized, and we set up the VM state. So we'll set the VM state here. We also give it pointers to the reset and realize functions. And then we set the properties using this. After that, so now we're going to create our own device. So when we call QDevNew, this is what it runs. It'll run this initialization function. Here is where you're going to initialize input and output GPIO, which is right here. And then input output clock signals right here. And then in sysbus devices, they have memory regions. Like here, we say our memory region uses these operations. And this is, so servo ops is going to be a struct that has basically just pointers to a function for reading and writing, and then the endianness of the system. And basically, anytime memory region is accessed via a read, it'll call the read function, and a write will call the write function. Give it a type, and then how big it is. Sysbus devices also initialize IRQs here. This one doesn't have any, but like any IRQ that connects to the NVIC is going to be defined here. Oh, and default values. So the pulse width here is a device variable that can be changed from the memory, so we set it here. So a little bit more about the sysbus devices and accessing their memory. We have the memory init function up here that we were discussing earlier, and there's the servo ops. So they are using memory region ops struct, which has pointers to a read and a write function, and then the endianness of the device. So the read function is going to take your offset and whatever value or however big you're reading it. And then in this case, we return for hex for offset 0, we return the pulse width, and then the write function is going to just do the same thing but with writing. So that's how those work. And then in realization, mostly it just checks that we use it for just checking the device state and creating any dynamic device properties like timers and clock signals. So here we check to make sure that the clock has a source, and then we create our 2 timers for the read and write of the UART. So after that, reset is called, and this is where we basically set all of the default values, make sure everything is ready for use, and the state is back to its initial state. So here we're clearing the data register and the baud rate registers. Some registers will have default values, like the control register, which starts at X300. But yeah, it's just resetting the device. Now moving on to machines. So a machine is a special device, which is basically just an entry point for QEMU. It uses its own special type info class init function. Um, this is how the user will activate, like start the code, basically. So this will put the machine in there so they can use it with the dash machine argument. So here we have the type info here. Its name is just a machine type name, and then the parent is a machine type, and then our class initialization function creates a machine class, which will have a description shown when you do help in QEMU. It'll like display the name and then the description next to it, and then it has an initialization function, and then it will um, have some things like this, and then the default CPU type should we use ARM. And then down here this is where we register the types. You do still have to do this for machines. This is gonna register the two different sheets. We have one for debugging and one for not debugging. In conclusion, that's the general gist of QEMU development. All of this information is shown here. We have a write-up with all of this in it. It's got everything you might need from running the emulator, debugging it, writing kernel code, and then all this information we're talking about here. We just talked about the header file, or the devices, machines, systems devices. And then next video is going to talk about interrupt requests and GPIOs. Thanks for watching.